Today, we will discuss carbohydrates. Do you ever think that a student quietly studying a textbook is aware that within his brain cells, billions of glucose molecules are splitting to provide the energy that permits him to learn? Glucose provides nearly all of the energy the human brain uses daily. Similarly, a marathon runner bursting across the finish line in an explosion of sweat and triumph seldom gives thanks to the glycogen fuel her muscles have devoted to help her finish the race. Together, glucose and its storage from glycogen provide about half of all the energy muscles and other body tissues use. The other half of the body's energy comes mostly from fat. People do not eat glucose and glycogen directly. Glycogen is the animal storage form of glucose. They eat foods rich in carbohydrates. Do not eat glucose and glycogen directly. They only eat foods rich in carbohydrates. Their bodies convert the carbohydrates mostly into glucose for immediate energy and into glycogen for reserve energy. All plant foods, whole grains, vegetables, legumes, and fruits provide ample carbohydrate. Milk also contains carbohydrates. Many people mistakenly think of carbohydrate as fattening and avoid them when trying to lose weight. Such a strategy may be helpful if the carbohydrates are the simple sugars of candy bars and cookies. But if the carbohydrates are the complex carbohydrates of whole grain, vegetables, and legumes, this strategy will not be working. First thing, you have to understand what is carbohydrate. Carbohydrate family include the simple carbohydrates, the sugars, and the complex carbohydrate, which is the starches and fiber. To understand the structure of carbohydrate, look at the units of which they are made. Each item can form a certain number of chemical bonds with other items. Carbon atoms can form 4 bonds, nitrogen atoms 3, oxygen atom 2, hydrogen atoms only 1. Only 4 main types of the atoms found in the nutrients are hydrogen, oxygen, nitrogen, and carbon. Each atom has a characteristic number of bonds it can form with other atoms. You can see here a graphical representation of carbohydrate classification. Carbohydrates are classified into 4 subclasses. First classification is monosaccharides, which is further classified in glucose, fructose, and galactose, which is the examples of monosaccharide. Second classification of carbohydrates are disaccharides. Sucrose, lactose, maltose are the examples of disaccharides. Third classification of carbohydrates are oligosaccharides. Raffinose and starchinose are the examples of the oligosaccharides. Polysaccharides are the last carbohydrate classification, which represents the starches, glycogen, and cellulose. What are the monosaccharides? Monosaccharide is the first classification of carbohydrates Monosaccharides, three monosaccharides are important in nutrition. All have the same numbers and kinds of atom, but all are in different arrangements of the atoms. These chemical differences account for the differencing sweetness of the monosaccharide. A pinch of purified glucose on the tongue gives only a mild sweet flavor, and galactose hardly tastes sweet at all. But fructose is an intensively sweet as honey, and is the sugar responsible for honey's sweetness. Glucose, fructose, and galactose. These are three types of monosaccharide. Glucose is a larger and more complicated molecule than the ethyl alcohol, but it obeys the same rules of chemistry. Each carbon atom has four bonds, each oxygen has two bonds, each hydrogen has one bond. It is the structure of the glucose. The structure of glucose has to be drawn flat, but in nature, the five carbons and oxygens are roughly in a plane. The atoms attached to the ring, carbons, extended above and below the plane. The diagram of a glucose molecules shows all the relationship between the atoms and proves symbol on examination. This figure shows how the chemical structure of glucose can be simplified by combining or omitting several symbols and still convey the same information. Glucose, commonly known as blood sugar, serves as an essential energy source for all the body's activity. Its significance to nutrition is tremendous. Glucose is one of the two sugars in every disaccharide and polysaccharide starch molecule. Starch is the chief food source of energy for the world's people, and other is glycogen, is an important storage form of energy in the body. Glucose is a simple sugar with the molecular formula C6H12O6. Glucose is the most abundant monosaccharide. Glucose is mainly made by the plants and most algae during photosynthesis from water and carbon dioxide, using energy from sunlight, where it is used to make cellulose in cell walls, the most abundant carbohydrates in the world. The glucose is the most important source of energy in all organisms. Glucose for metabolism is stored as a polymer in plants, mainly as starch and amylopectin, and in animals as glycogen. Glucose circulates in the blood of animals as blood sugar. The naturally occurring form of glucose is D-glucose, while L-glucose is produced synthetically in comparatively small amounts and is less biologically active. Glucose is a monosaccharide. Glucose molecule can exist in an open chain as well as ring form. Glucose is naturally occurring and is found in its free state in fruits and other parts of plants. Glucose is released from the breakdown of the glycogen in a process known as glycogenolysis. Glucose forms white or colorless solids that are highly soluble in water and acidic but poorly soluble in methanol and ethanol. Glucose is usually present in solid form as a monohydrate with a glucose closed pyrene ring. The open chain form of glucose makes up less than 0.02% of the glucose molecules in an aqueous solution. The rest is one of two cyclic hemiacetal forms. In its open chain form, the glucose molecule has an open unbranched backbone of 6 carbon atoms, where C1 is part of an aldehyde group. Glucose is also classified as an aldose, aldohexose. The aldehyde group makes glucose a reducing sugar, giving a positive reaction with the Verhelling test. The open chain of the open chain form of glucose exists with several cyclic isomers, each containing a ring of carbon closed by one oxygen atom. More than 99% of glucose molecules exist as pyranose form. The open chain form is limited to about 0.25% and furanose forms exist in negligible amounts. The term glucose and D-glucose are generally used for these cyclic form as well. Fructose is an abundant monosaccharide in the human diet that the body needs to metabolize. Their consumption results in a significant amount of added sugars entering the diet, approximately half of which is fructose. Sucrose converted into fructose and glucose by acid hydrolysis in the stomach and sucrase isomaltase cleavage in the small intestine. Transport and metabolism of fructose do not require insulin. Only a few tissues such as liver, intestine, kidney, adipose tissues, and muscles can metabolize it. Glucose and fructose have similar metabolic rates because most of the dietary fructose converts into the glucose. Fructose is the sweetest of the sugars. Fructose has exactly the same chemical formula as glucose, C6H12O6, but its structure differs. The arrangement of the atoms in fructose stimulates the taste buds on the tongue to produce the sweet sensation. Fructose occurs naturally in fruits and honey. Other sources include products such as soft drinks, ready-to cereals, and desserts that have been sweetened with high fructose corn syrup. Fructose along with glucose. It also occurs in certain vegetables. It is a component along with glucose of the disaccharide sucrose or common table sugar. Phosphate derivatives of fructose are important in the metabolism of carbohydrate. Structure of the fructose, like all simple sugars. You can see here the graphical representation of fructose. Fructose can be expressed as a 6-carbon linear chain with hydroxyl and carbonyl groups. In its crystalline form and in solution, most of it exists as two hemiketal rings, beta-D-fructopyranose and beta-D-fructofuranose. In aqueous solution, it consists of 70% pyranose, 22% furanose, and smaller amounts of the linear and other cyclic forms. Fructose is the most water-soluble monosaccharide. It dissolves in exceedingly small amounts of water. This property makes it difficult to crystallize from water and accounts for its hygroscopicity and hematoxin. Fructose was discovered by French chemist Augustin Pierre de Brenfont in 1847. Consumption of the excessive quantities of the foods that contain fructose and other sugars is a well-known cause of type 2 diabetes, elevated level of LDL, cholesterol, and triglycerides, and of course, obesity. But fructose may be slightly safer than the others, especially for the diabetics because it has a lower glycemic index than sucrose and is considerably sweeter. When sugar comes to mind, you probably think of table sugar or sucrose. But the simple carbohydrate is made up of even smaller sugar molecules called glucose, and fructose is an exact 50-50 split. Glucose and fructose are both monosaccharides, sugar molecules in the simplest form. The body's preferred sources of the fuel is glucose. Glucose is sourced by breaking down disaccharides or polysaccharides, which are larger sugar molecules. Fructose is found in its simplest form in fruits and some vegetables like corn, potatoes, and beets. Both glucose and fructose are carbohydrate, but not all carbohydrates are created equal. When we eat sucrose, the glucose and fructose molecules become split inside the body. The main difference between the glucose and fructose for our purpose is how they are processed within your body. You may notice that all these foods, which include rice, oats, breads, pasta, and starchy vegetables, are pretty filling. This is because glucose, after being absorbed by the small intestine, raises blood sugar levels. This stimulates the production of insulin, which in turn induces the creation and secretion of leptin. Leptin is known as the fullness hormone, and is that it does not exactly what it sounds like it does, makes you feel full. When we talk about blood sugar, we are actually referring to the blood glucose. This is the amount of the glucose in your bloodstream. The glucose travels through the bloodstream, providing energy to all the tissues in your body that need it. Common sources of fructose include fruits, honey, soft drinks, and vegetables. Fructose changes blood sugar levels much more gradually than the glucose and does not seem to impact insulin level. Unlike glucose, which is processed throughout the whole body, fructose is almost entirely metabolized by the liver. Overconsumption can cause fatty liver and visceral fat around essential organs. While glucose stimulates the fullness hormone, fructose may do the opposite. Fructose contributes to the pattern of overeating. If you don't feel full, you will just keep on eating. Fruits are nutritionally dense, containing numerous vitamins, minerals, antioxidants, and polyphenols. The diet rich in fruits and vegetables are associated with low rates of heart diseases, diabetes, and strokes. Majority of your carbohydrates should come from the vegetables rather than fruits. Fructose from fruits may be okay for most people. With diabetes should be way rare. The monosaccharide galactose rarely occur as a single sugar. Galactose has the same number and kinds of the atoms as glucose and fructose in another arrangement. Galactose was first isolated by Louis Pasteur in 1855 from milk. Its structure was clarified 30 years later by the Morrell R. and Fisher E. In 1860, Prothlot named it as lactic glucose or galactose, from the Greek galactose, which means milk. It occurs in the both open chain and cyclic form. The open chain form of has a carbonyl group at one end of the chain, which makes it an aldehyde derivative, therefore an aldohexose and reducing sugar. In the cyclic form, it has four stereoisomers. The main dietary source is the disaccharide lactose, which is made up of galactose molecule and a glucose molecule, joined by a beta L-Val4 glycosidic bond. In the small intestine, glycosidic bond is hydrolyzed in a reaction catalyzed by lactase to produce galactose and glucose, which are the absorbed. It performs a wide range of functions. The open chain form is thermodynamically unstable and is present in trace amounts in solution. Aldehydes can react with alcohols, so the linear form of glucose, galactose, can cyclize via nucleophilic attack by the oxygen atom of one of the hydroxyl group to the carbon atom of the carbonyl group to form an intramolecular hemiacetal. Cyclic compounds with a ring consisting of 3 or 4 atoms are less stable than those containing of 5 and above all 6 atoms due to high steric interactions like the cyclic alkanes, cyclopropane and cyclobutane, which are less stable than cyclopentane and cyclohexane. In the cyclic form, galactose exists as 4 stereoisomers to have a 5-membered ring consisting of one oxygen atom and 4 carbon atoms, a furanose ring, and 2 have a 6-membered ring consisting of one oxygen atom and 5 carbon atoms, a pyranose ring. In solution, pyranose and furanose forms are in equilibrium with the open chain form, but since the furanose form is less stable than the pyranose form, the equilibrium is strongly shifted towards the latter. The only cyclic form found in mammals is the pyranose form, which is the epimer of the glucose, as it differs only by the configuration of the hydroxyl group on the C4. The furanose form is found in many lower organisms, both prokaryotics and eukaryotics such as bacteria, green algae, fungi, protozoa. Furanose form is also found in the pathogenic species, where it may play an important role. For example, for survival, while its biosynthetic pathway may be a target for the development of new drugs to treat infection caused by these pathogens. Before talking about the disaccharides, firstly we have a look on condensation and hydrolysis. Hydrolysis is any chemical reaction in which a molecule of water breaks one or more chemical bonds. Biological hydrolysis is the cleavage of biomolecules where a water molecule is consumed to effect the separation of a larger molecule into component parts. When a carbohydrate is broken into its component sugar molecules by hydrolysis, for example, being broken down into glucose and fructose. Hydrolysis reactions can be reserved for a condensation reaction in which two molecules join into a larger one and eject a water molecule. Hydrolysis adds water to break down, whereas condensation built up by removing the water is basically a breakdown a disaccharide into a chemical reaction known as hydrolysis. A molecule of water splits to provide the hydrogen and hydroxyl group needed to complete the resulting monosaccharides. Hydrolysis reactions commonly occur during the digestion, and condensation is about making of a disaccharide. A chemical reaction known as condensation link two monosaccharides together, a hydroxyl group from one monosaccharide and a hydrogen atom from the other combine to form a molecule of water. The two separate monosaccharides link together with a single oxygen, called a double sugar, is a molecule formed by two monosaccharides or simple sugars. Three common disaccharides are sucrose, maltose, and lactose. They have 12 carbon atoms and their chemical formula is C12H22O11. The less other common disaccharides include lactulose, trehalose, and cellulose. Disaccharides are formed through dehydration reactions in which a total of one water molecule is removed from the two monosaccharides. Disaccharides are basically the carbohydrates found in many foods and are often added as sweetener. Sucrose, for example, is a table sugar, and it is the most common disaccharide that humans eat. It is also found in other foods like beetroot. When disaccharides like sucrose are digested, they are broken down into their simple sugars and used for energy. Lactose is found in breast milk and provides nutrition for infants. Maltose is sweeter that it often found in chocolates and other candies. Plants store energy in the form of the disaccharides, like sucrose, and it is also used for transporting the nutrients in the phloem. It is an energy storage sources. Many plants, such as sugarcane, are high in sucrose. Trehalose is used for transport in some algae and fungi. Plants also store energy in polysaccharides, which are many monosaccharides put together. Starch is the most common polysaccharide used for storage in plants, and it is broken down into maltose. Plants also use disaccharides to transport monosaccharides like glucose, fructose, and galactose between cells. Packaging monosaccharides into disaccharides makes the molecule less likely to break down during transport. You can see in this picture how a glucose molecule and a fructose molecule combine to form a sucrose molecule. A hydrogen atom from one molecule and a hydroxyl group from the other molecule are eliminated as water, with the resulting covalent bond linking the two sugars together at that point. Sucrose is commonly known as table sugar, as you all know, is the example of the disaccharide. Disaccharide is a carbohydrate formed by the joining of two monosaccharides. Other common disaccharides include lactose and maltose. Lactose is formed from glucose and galactose, while maltose is formed from two glucose molecules. Are short chain made up of smaller sugar molecules that act as building blocks. Maltose is made of two glucose units. Table sugar, also known as sucrose, is made of the glucose and one fructose molecule. Maltose can be made by the breakdown of the starches, a long chain of many glucose units. Plant seeds also produce enzymes to release sugar from starch as they sprout. People have long taken advantage of this natural process for food production. For example, in the process of melting, graining are sprouted in water then dried. This activates the enzymes in the grains to release maltose and other sugars and proteins. The sugars and proteins in malt are very nourishing for yeast, so malt has become important in brewing beer and malt vinegar. Malted grains are also used in candies and desserts as sweeteners. Maltose can be purchased as dry crystals, where brewing supplies are sold, or as a syrup sold alongside baking supplies. The syrup is usually corn based, but it's not to be mistaken for high fructose corn syrup. You can use maltose in your recipes as a one-one substitute for other sugars. Maltose is not as sweet as sucrose or fructose, or in some recipes, slightly more than 1-1 may be needed to produce the desired flavor. Several foods naturally contain the maltose. You can find it in wheat, cornmeal, barley, and several grains. Many breakfast cereals also use malted grains to add natural sweetness. Fruits are another common sources of the maltose in the diet, especially peaches and pear. Sweet potatoes consider and contain the more maltose than most other foods. Most syrups get their sweetness from maltose. High maltose corn syrup provide 50% or more of its sugar in the form of maltose. It is useful in making hard candies and an inexpensive sweetener. People commonly use sucrose for cooking and sweetening foods. It's another short two-sugar chain made of one glucose molecule linked to one fructose molecule. Because sucrose delivers both these sugars, its health effects are likely somewhere in between those of glucose and fructose. Fructose has more several health implications and is metabolized differently than glucose. Consuming a high fructose diet may cause a quicker onset of obesity, insulin resistance, and diabetes. Maltose is made up of just glucose, not fructose. It might be slightly healthier than table sugar. Most maltose is broken down into glucose when digested. Its health effects are probably similar to other sources of glucose. Nutritionally, maltose provides the same number of calories as starches and other sugars. Your muscles, liver, and brain can convert the glucose into energy. In fact, your brain gets its energy almost exclusively from glucose. Once these energy needs are met, any remaining glucose in your bloodstream is converted into the lipid and stored as fat. As with other sugars, when you consume the maltose in moderation, your body uses it for energy and it does not cause harm. If you consume maltose in excess, it can lead to obesity, diabetes, and heart kidney diseases, just like other sugars. For maltose, as for most nutrient, it's the dose that makes the poison. And glucose together form sucrose. Because the fructose is in a position accessible to the taste receptors. Sours taste sweet, accounting for some of the natural sweetness of fruits, vegetables, and grains. To make table sugar, sucrose is refined from the juices of sugar cane and the sugar beets, then granulated, depending on the extent to which it is refined. The product becomes the familiar brown, white, and powdered sugars available at grocery stores. Sucrose is organic compound, colorless, sweet-tasting crystals that dissolves in water. Its formula is C12H22O11, hydrolyzed by the enzyme invertase, yields invert sugars, so called because the hydrolysis results in an inversion of the rotation of plane polarized light. Sucrose occurs naturally in sugarcane, sugar beets, sugar maple sap, dates, and honey. It is produced commercially in large amount. especially from sugarcane and sugar beet. Sucrose is the scientific name of the table sugar. Sucrose is a disaccharide consisting of one glucose and one fructose molecule, 50% glucose and 50% fructose. Since sucrose is a disaccharide, it must be broken down before your body can use it. Enzymes in your mouth partially break down sucrose into glucose and fructose. The majority of the sugar digestion happens in the small intestine. The enzyme sucrase, which is made by the lining of your small intestine, splits sucrose into glucose and fructose. The presence of glucose increases the amount of fructose that is absorbed and also stimulates the release of insulin. This means that fructose is used to create the fat compared to when this type of sugar is eaten alone. Eating fructose and glucose together may harm your health more than eating them separately. Most people are aware that sugar is added to foods and beverages to provide the sweetness. But many may not know that sugar is also used for many other reasons. Sugar is a common ingredient in baked goods to provide structure and texture in homemade jams and jellies, to act as preservative, and in other items to stabilize emulsions and flavor. These attributes give many of our favorite foods that taste and mouthfeel we have come to expect. Lactose is referred to as milk sugar because it only found naturally in the milk of mammals, including cows, goats, and humans. Milk from cows and goats is used to make cheese and yogurt, but not all milk products contain the same amount of lactose. For example, hard cheese such as cheddar, parmesan, and Swiss contain very little or no lactose, whereas milk, ice cream, and yogurt contain higher amounts of lactose. Hard cheese are lower in lactose due to the removal of whey. Whey is a liquid solution of fat, lactose, and proteins, while they are being made as well as the continued breakdown of lactose by bacteria during the aging process. The combination of galactose and glucose makes the lactose, the principal carbohydrate of milk. Lactose contributes about 5% of milk. Depending on the milk fat content, lactose contribute 30 to 50% of milk sugar. The sugar that we consume is often described as either natural sugars or added sugar. Like many other types of the sugars, lactose can be considered both a natural sugar and an added sugar, depending on its sources. Lactose is inherent to the milk of mammals and can also be isolated from this original source and crystallized for use as an ingredient in foods such as baked goods, caramels, frozen desserts, fudge, meat products, sauces, and soups. The lactose found in plain milk and plain milk product is considered a natural sugar, whereas the lactose that is added to packaged foods and beverages as an ingredient during manufacturing is considered an added sugar. Lactose digestion occurs in the small intestine with the help of the enzyme known as lactase. Lactase breaks down lactose into the monosaccharide galactose and glucose, which makes them available for absorption. Glucose ultimately gets taken up by our cells with the help of insulin. Galactose is transported to the liver, where it is turned into glucose for use in energy production. Because of critical nutrition that lactose in breast milk provides to infants, we are born with the ability to produce lactase. Only in rare instances are infants born with lactase deficiency, a condition called congenital alactasia. Infancy is the life stage when lactase production is high. After weaning, lactase production quickly and drastically slows and typically diminishes as we age. This decrease in lactase production can result in the inability to digest lactose later in life. Not everyone who has difficulty digesting the lactose experiencing the same symptoms, nor are they all considered the lactose intolerance. Lactose intolerance is a condition that stems from the body not producing enough lactase and results in the expression of physical symptoms such as abdominal bloating and cramps, diarrhea, and gas. Lactase production is the biological process that is determined by our DNA. The prevalence of lactose intolerance is highest among those of East Asian descent and lowest among those of the Northern European descent. Having an intolerance for the lactose is not the same as having a milk allergy. Allergic reactions to milk are the immune system's response to the protein in milk. Whey proteins and casein proteins are the proteins of the milk. Lactose intolerance stems from low lactase production and results in physical responses from the digestive system. It is important to know the difference between a food allergy and an intolerance. What are oligosaccharides? Oligosaccharides are the third classification of carbohydrates. Oligosaccharide means a few saccharides. A saccharide refers to the unit structure of carbohydrate. Oligosaccharide is a carbohydrate comprised of a few saccharides, that is about 3 to 10 saccharide units. The number of monomer units in an oligosaccharide is not rigorously defined. Similar to other carbohydrates, oligosaccharides are made up of hydrogen, carbon, and oxygen. An oligosaccharide has a longer chain of saccharide monomeric units than a monosaccharide comprised of only one saccharide unit, or a disaccharide comprised of two saccharides. It is relatively smaller than a polysaccharide, which is comprised of more than 10 saccharide units. The chemical process of joining monosaccharides unit is dehydration synthesis since it results in the release of water as byproduct. The oligosaccharides is formed by the joining of monosaccharide units via glycosidic bonds. Glycosidic bonds are covalent bonds that may form between the hydroxyl groups of two monosaccharides. Many of the naturally occurring oligosaccharides are linked to other biomolecules, such as proteins, peptides, and lipids. Carbohydrates that are covalently linked to another biomolecule via glycosylation are referred to as glycoconjugates, and the carbohydrate constitute of the complex is called a glycan. Glycolipid is a carbohydrate. Certain oligosaccharides and polysaccharides attached to a lipid. A glycoprotein is a carbohydrate attached to a protein. Oligosaccharides may be classified based on the number of monosaccharides they contain. Trisaccharides are oligosaccharides. comprised of three monosaccharides, which are nig- nitrotriose, three glucose units joined by alpha 1,3 glycosidic linkage; maltotriose, three glucose units joined by 1,4 glycosidic linkage; malazatose, glucose, fructose, and glucose are linked together; maltotrilose, glucose, glucose, and fructose molecules are linked together; raffinose, galactose, glucose, and fructose are linked together to form the molecule of oligosaccharide raffinose; gastose, glucose, fructose, and fructose are linked together to form the oligosaccharide gastose. Tetrasaccharides. What are tetrasaccharides? Tetrasaccharides are oligosaccharides comprised of four monosaccharides: maltotetraose, four glucose units joined by 1,4 glycosidic linkage; statiose, galactose, glucose, fructose molecules are linked together to form the oligosaccharide statiose; sesame comprises of galactose, fructose, and glucose molecule. Pentasaccharides are those comprised of five sugar units. N-linked oligosaccharides are mostly pentasaccharides. Hexasaccharides are oligosaccharides comprised of six sugar units. Alpha-cyclodextrin is an example. It consists of six glucose units linked via alpha-1,4 linkages. Heptasaccharides are oligosaccharides containing seven sugar units. Octasaccharides contain eight. Nanasaccharides have nine. Decasaccharides have 10, and so on. Raffinose is a trisaccharide composed of galactose, glucose, and fructose. It can be found in beans, cabbage, Brussels sprouts, broccoli, and vegetables, and whole grains. Raffinose can be hydrolyzed to D-galactose and sucrose by the enzyme alpha-galactosidase, an enzyme not found in the human digestive tract. The raffinose family of oligosaccharides are alpha-galactosyl derivatives of sucrose, and the most common are the trisaccharide raffinose, the tetrasaccharide stachinose, and the pentasaccharide verbascose. Raffinose are almost ubiquitous in the plant kingdom, being found in a large variety of seeds from many different families, and they rank second only to sucrose in abundance as soluble carbohydrate. Raffinose may have a form of white crystalline powder. It is odorless and has a taste approximately 10% that of sucrose. Stachyose is a tetrasaccharide consisting of two alpha-D-galactose units, one alpha-D-glucose unit, and one beta-D-fructose unit, sequentially linked as alpha-1,6, alpha-1,6, alpha-1,2 beta. Together with related oligosaccharides such as raffinose, stachinose occur naturally in numerous vegetables such as green beans, soybeans and other plants. Stachinose is less sweet than sucrose at about 28% on a weight base. It is mainly used as a bulk sweetener or for its functional oligosaccharide properties. Statiose is not completely digestible by the humans and delivers 1.5 to 2.4 kilocalories per gram.